Here's where we are today, just to do some process check. We have 2 more lectures, and we'll be done with continuous, this first analysis of the continuous system. We're going to look at the response. Today I'm going to finish the total response, and we're going to do some more applications next class. So that would be today's lecture and next lecture. After that, which means next Thursday, we're going to have a first review sessions. And I'm going to be doing nothing but problems. Right? I'm going to be selecting probably 7, 8 problems and do them here. They're going to be in the notes. I'll post the review session as well on the website. But what I would like to do is, since these problems are going to be solved anyway, and the notes are going to be there, I would like you to bring in the problems that you tried to solve and you didn't manage to solve. So then we'll try to solve them here. And that way you're going to have the problems I've solved plus the problems that we solved here in real time during the lecture. So you have all of your homework. You know, I hope, and actually I'm almost sure you try to solve a lot of them, if not all. If you ran into some problems, you know, let's go through them next Thursday. Right? So that would be the first. And then what I was kind of thinking, when we come next Thursday, then I'll tell you when we're going to have the first midterm exam. Because remember, there are 2 exams and then final in this course. All right. So let's continue where we left off last time. Last lecture ended up on a high note. We discovered convolution. So let's play with it today, kind of discover its properties and talk about them in more detail. So I guess here convolution integrals. So here's the settings, our standard settings. We have a system that that is a linear time invariant system. We know that if we present delta pulse to the system will respond to h of t. And we know if we present x of t, the output is going to be y of t. We also know the differential equation for this system that says that q of t operating on your y of t is going to be t of t operating on x of t. Those are those polynomial operators. Now, our goal here is to determine what y of t is for an arbitrary x of t, right? So I want to understand if by knowing delta of t, by knowing h of t, if I can calculate y of t for an arbitrary x of t. What we did last time, let me just give you a 2-sentence summary here. We actually took our signal x of t, which is a continuous time signal, analog, and we approximated the signal with a whole bunch of first square pulses, ended up with this signal x hat of t, and x hat of t was given as x hat of t was given as a sum over n of x of n t divided by delta t times p of t minus s delta t times delta t. Essentially approximating this signal x of t as a bunch of square pulses. Now, this delta t is the width of this pulse. And it is clear that as delta t goes to 0, then these pulses become narrower and narrower, and they actually become the difference between x hat of t and x of t becomes negative. And what we discovered after some math, we discovered that as delta t goes to 0, then this x of t could be seen as an integral when tau goes from minus infinity to plus infinity. And I know how we write integrals, but let me write it slightly different with x of tau d tau times delta of t minus tau, right? To be essentially kind of close to this formulation here. So now, what happened here is that our this part and this part, as delta t goes to 0, becomes a delta, right? You can see that this pulse becomes narrower and narrower, right? But this height becomes higher and higher, right? And the area under the curve is essentially this p and this delta t combined to give me delta, and this x of n of t dt combined to give me the area under the pulse. And what this teaches me is that I can decompose my input as a whole bunch of pulses coming one after the other. They're coming very close. The distance between them is infinitesimally small. It's delta tau, right? So they're coming right after one another. The area under each one of the impulse is x of tau, d tau, and they continuously build my input function. Now, that's a big insight in what how you can see the input. Now, what I bring to my help now is a superposition. And I know that the system is linear, the superposition holds. So instead of now looking at all of these pulses, let me look at one. And then I know from our analysis that if I hit my system with an impulse, I get an impulse response. So now by the virtue of the superpositions, all of these impulses at the input produce impulse responses in the output. And it's straightforward to write the output equation. We're saying that y of t is going to be integral when tau goes from minus infinity to plus infinity, x of tau d tau h of t minus tau, right? Because every one of these impulses creates an impulse response, right? And it's scaled by whatever is the magnitude of the input impulse, and the magnitude is x of tau d tau. Now, the same magnitude here, but now for every one of the impulses, you get an impulse response. And now this becomes, commonly written as tau goes from minus infinity to plus infinity, x of tau h of t minus tau d tau, right? And we call that convolution integral. Another common notation is to avoid the cumbersome writing here with integrals and stuff. We use common notation x of t star h of t to indicate that you're taking convolution between two signals in the time domain. So you can understand convolution integral as essentially manifestation of your superposition, right? It tells you, okay, the way how you can understand the output of this system is it's going to be summation of all the impulse responses coming from your input signal. Impulses and the input signal can also be seen as a bunch of impulses coming one after the other. So now that we have defined this integral, it's instructive to go over some of its properties, because really, we came here from physics on this whole situation. We came, out of the differential equations, and we kind of attached the physical, distinct physical interpretation to the terms of these integrals. But at this point, really, it becomes just an integral transform. I feed in x of t into a transform h of t, and as an integral transform, it has some properties that are good to know. Actually, they're pretty much required to know, because we're going to use this integral over and over to gain more and more insight into properties of the linear system. So let me go over 3-4 fundamental properties. They're all relatively easy, and we're going to kind of breeze through them. I'm going to try to spend and give some insight in a couple of them that require a little bit more explanation. So properties of convolution integral. So I have two time domain functions. x of t and y of t. And I define x of t convolved with y of t. Oh, sorry, not y of t. x1 of t and x2. x1, x2, x1 convolved with x2 of t. I define it as integral when tau goes from minus infinity to plus infinity, x1 of tau times x2 of t minus tau d tau. And I call that convolution integral. Convolution as an operation occurs in other fields outside of this. So the way how these properties are stated, I just have two functions that without explicit reference that this is input and this is an impulse response, right? It can be any two functions, and I'm just performing this operation on the two of them. So what are the properties? The first one is commutative property. And this one says that x1 of t convolved with x2 of t is the same as x2 of t convolved with x1 of t, right? Essentially saying that you can change the order in which you do your convolution, right? All of these properties have relatively easy proofs. So I'm going to prove this one, and I think your book proves all of them. But I'm going to skip some of them that are relatively easy and straightforward. So how would one prove this? Well, you start by saying x1 of t convolved with x2 of t. You know, by definition, it's an integral when tau goes from minus infinity to plus infinity. x1 of tau, x2 of t minus tau d tau. Now I'm going to introduce the substitution. Substitution, where I call tau minus t equal to z. From here, you get that tau is equal to t minus z, and d tau is equal to minus dz. So let's substitute that back in this equation here. So x1 of t convolved with x2 of t becomes equal. Now, when tau is at minus infinity, where is z? If this is minus infinity, t is a constant, right? So where is z? Look at it here. If tau is minus infinity, where is z?
Plus infinity.
Plus infinity, right? So z now goes from plus infinity to minus infinity. Now I have x1 of tau, tau is t minus z, x1 of t minus z, x2 of z, and then instead of tau I have minus dz. Okay? And then you can see this minus here flips the borders back, so this becomes an integral when z goes from minus infinity to plus infinity, x1 of t minus z, x2 of z, dz, which is the same as saying this is x2 of t convolved with x1 of t, right? Because I can switch the order here. Z is just a dummy variable, so it's irrelevant whether it's z or tau. It doesn't matter. So this is how one would prove this. So the convolution is commutative. You can actually change the order in which you do convolution. There are two other properties that are kind of the same nature and very easy to prove. So I'm just going to state them. So the first one is distributive property. And And this one says that x1 of t convolved with x2 of t plus x3 of t is equal to x1 of t convolved with x2 of t plus x1 of t convolved with x3 of t. Very easy to understand it. It's a consequence of distributive properties of the integration. Right? Remember, this is a hidden integral. If you have a subintegral function that's the sum of the two functions, then this would split into two integrals and kind of give you right away this conclusion here. The third one is associative property. And this one says that if you have x1 of t convolving x2 of t, that is convolved with x3 of t, then you can actually change the order in which you do the convolution and first do x1 of t times convolved with x2 of t, and then convolve the result with x3 of t. Right, so you can this is all again consequence of integral nature of this operation. Fourth property is shift property. Now, consider now that I have two signals, x1 of t convolved with x2 of t, and the result of that convolution is c of t. What happens if one of the signal is delayed by some capital T? So for example, if I take now x1 of t convolved with x2, but delayed by capital T, the result is c of t minus capital T. It's a linear operation. Remember, this is a linear system. Superposition holds. So if I take the second signal, let's imagine that this is an impulse, that this is an input, and this is an impulse response. If I delay input by t, the output is going to be delayed by the same t, right? So it's relatively easy to understand in settings of the linear system. Also, if I have x1 of t minus capital T, and then x2 of t minus capital T, the result is going to be c, let's say t1 and t2 is going to be t minus t1 minus t2. So if I delay the first one by t1 and second by t2, the overall delay and the output is going to be the sum of the two delays. Let me quickly prove this one. It's easy to solve. One. x1 of t convolved with x2 of t is equal to integral when tau goes from minus infinity to plus infinity, x1 of tau, x2 of t minus tau d tau. Now if I delay the second one here, put x2 of t minus tau, x1 of t convolved with x2 of t minus capital T is an integral when tau goes from minus infinity plus infinity, x1 of tau, x2 of t minus capital T minus tau d tau. Just a straightforward implementation of the definition of the convolution integral. Now I'm going to introduce the substitution where t minus capital T minus tau is going to be a new variable, which I'm going to call nu. From here, you can see what do we need? We need tau. So tau is going to be t minus capital T minus nu, and d tau is going to be minus d nu. Actually, I don't need to even go this far. Let's just do this substitution t minus capital T is equal to nu. So then I have x1 of t convolved with x2 of t minus capital T is going to be integral of tau goes from minus infinity plus infinity, x1 of tau, x2 of nu minus tau d tau, right? And now if you compare this against this thing here, you can see that the result of that is C of nu. And then when I put back what the nu actually is, this is C of t minus t capital lowercase t minus capital T. Just a little formal approach to this definition. So the interpretation is very easy. If you delay one of the signals, the output is going to be delayed. If you delay both of the signals, then the delay in the output is going to be sum of the delays of both of the signals. The next one is extremely useful property. It's a width property. And here's what this property says. If x1 of t and x2 of t are finite in time, okay, you have two signals that are finite in time, and let's say duration of x1 of t, x1 of t is t1, and duration of x2 of t is t2. Then duration x1 of t convolved with x2 of t is equal to is t1 plus t2. Let me sketch what is meant by this. If I have a first signal, let's say this is t and this is x1 of t, and let's say this is how the first signal looks like. Its complete duration here is t1, and I have another signal that looks like this, and its duration here is t2, that's x2 of t. Well, if I convolve these two signals, I get the resulting signal. Let's say, right? The total duration of this one is t1 plus t2. Now, this is, if you think about one of them as being an input and the other one being impulse response, this tells you how long in the time domain is going to be the output signal. We run into this all the time. For example, we use this and kind of think about this all the time in a digital communication. Let's say this is your bit or symbol, and let's say this is the impulse response of the channel. The duration of this T1 plus T2 tells you the dispersion in the output. Tells you, for example, how many bits or symbols after the one that you're receiving are going to be corrupted with the one that you're currently receiving. Let's say the channel has an excessive delay. Your age of t for the channel is pretty long. That puts a fundamental limit on your communication. So if I send you a symbol and it takes you 3 symbols to receive, 3 times the duration of the symbols to receive, then I shouldn't really send you a new one, because before you finish the reception of the previous one. So that limits on how many symbols per second I can send. That's just a first cut idea here, but we have a lot of ways of dealing with and still preserving the symbols. But this is the physical meaning of this property here. So far, I have not imposed any restrictions on x1 of t and x2 of t. I said these are just arbitrary functions of time. Now, in most practical situations, x1 of t and x2 of t, in our scenario here, are going to be either inputs or they're going to be impulse responses of the system. Most of the time, these two are going to be causal, which means that for some suitably defined time, they're not going to start before something, right? You cannot have an input before 0, or your impulse response cannot appear before you actually present an input in most causal systems. If that's the case, so if x1 of t and x2 of t are causal, meaning they don't exist before 0, before t equals 0, the convolution integral simplifies. And I can say here x1 of t convolved with x2 of t is going to be integral from 0 to t, x1 of tau, x2 of t minus tau d tau. Usually we put 0 minus here to include the potential initial conditions at t equal to 0. Of course, we can rewrite this in using the commutative property of so this is tau goes from 0 minus to t, x2 of tau, x1 of t minus tau d tau. And we use this property quite often to simplify the calculations, right? Along with this commutative. Sometimes it's easier to look at it this way, sometimes it's easier to look at it this way. Which one you actually look at is a function of which one gives you the shortest path to the solution. So let me work through an example here that illustrates some of these properties here. I'm looking at example 2.5, and I have a linear time invariant system with an impulse response, h of t, given as e to the minus 2t u of t. U of t here is explicitly indicating that this is a causal system, right? The impulse response does not exist before t equals 0. If I leave it without it, then this is essentially a function that exists for all t, or has a value that's non-zero for all t. This function here has value 0 for every time t is smaller than 0. Now the input presented to the system, x of t is equal to e to the minus t u of t. And the question is determine y out. Now, y of t is x of t convolved with h of t. Right, and in long form, this is an integral. When tau goes from minus infinity to plus infinity, x of tau, y of t minus tau, d tau. So all of these problems, there's going to be quite a few of these problems that you're going to have for your homework and in general. And I always kind of suggest always write out what is it that you need to calculate. Don't be afraid to kind of spell it out. And now you say, well, this is what I need to calculate. So let me put these in here, and then we'll see where it leads us, right? You always leave the boundaries, as they are. So this becomes an integral when tau goes from minus infinity to plus infinity. The first one is x of tau, so it's e to the minus tau u of tau, right? Because remember, x of tau is this whole thing, not just e to the minus
Excuse me?
No, go ahead.
Is that y t minus tau or h t in the last line? Y t is
H,
oh,
H, sorry. Yeah, sorry. H, your impulse response. Now, h of t minus tau is e to the minus 2 t minus tau u of t minus tau d tau. Okay? So far, we haven't been doing anything really smart. We're just making sure that we don't make mistakes in the substitution. So let's now look at the subintegral function and fix our borders, right, over which we need to integrate. So now we look at, there are two functions here that will tell us what our borders need to be. This one and this one. What happens to u of tau when tau is smaller than 0? U of tau is 0. So is there a need to integrate anything before 0? No. So this tells me what the first boundary is. So this is an integral when tau goes from 0. Now let's look at the other one. Now let's start increasing the value of the tau here. Whenever tau is smaller than t minus tau is positive. U of something positive is 1. But when tau exceeds t minus tau becomes negative, u of negative number is 0. So therefore, there's no need to integrate beyond t, right? So this becomes integral from tau equals 0 to t, and then I have e to the minus tau, e to the minus 2 t minus tau d tau. And now this is an easy integral. You can see that e to the minus t can come outside because it does not depend on tau. And inside I have e to the minus tau plus 2 tau. So this ends up being e to the minus 2t. Integral tau goes from 0 to t, e to the tau d tau. And this is just about the easiest integral to evaluate. This is e to the minus 2t, e to the t, integral into the, tau, when tau goes from 0 to t. So this is e to the minus 2t, e to the t minus 1. Or when you bring this e to the minus 2t inside, this becomes e to the minus t minus e to the minus 2t. Now, we've dropped these u of t's here, right? But now, as a result, you end up with this expression that appears to be valid for all t. Is that the case? No. This is valid only when?
Positive 0
When t is greater than 0, right? So really, your output y of t is going to be e to the minus t minus e to the minus 2t times u of t. Right? So that's the output. And the output is also causal. If you have an input that is causal and impulse response that is causal, the output is causal as well. Okay, so just aside, let me cover, so far we've been working mostly with linear inputs and impulse responses. We assume that all our signals are linear. There's this is just for the sake of simplification. There is, all of what we've covered pretty much holds for complex numbers as well, or complex signals as well. So let me just cover that as another thing here. So response to complex inputs. Just cover how you do convolution if your signals are complex. So let's assume that x of t is complex. So x of t is x real of t plus j x imaginary of t. And your age of t is complex 2. So you can say age of t is equal to age real of t plus j x imaginary of t. Now, x of t convolved with age of t becomes, in this case, x real of t plus j x imaginary of t convolved with age real of t plus j x imaginary of t. That's our star notation. In a complex notation, nothing changes. In a long form notation, integral notation, nothing changes. Here you're going to be integrating tau goes from minus infinity to plus infinity. X of tau, so it's going to be x real of tau plus j x imaginary of tau. And then I multiply that with age of t minus tau, which in our case becomes x real of t minus tau plus j x imaginary of t minus tau, d tau. And then you can see that as a result of this, you end up with 4 terms that look like this. The first term is tau goes from minus infinity to plus infinity, x real of tau, age real of t minus tau, minus d tau, minus integral tau goes from minus infinity to plus infinity, x imaginary of tau times age imaginary of t minus tau, d tau. Where is the minus from? J times j gives me this minus, right? And two other terms are plus j, integral tau goes from minus infinity to plus infinity, x real of tau times h imaginary t minus tau, d tau, and then plus then integral when tau goes from minus infinity to plus infinity, x imaginary of tau, h real of t minus tau, d tau. So complex convolution ends up being just a linear combination of the real ones. So by knowing how to evaluate the real convolution, there's no mystery about the complex convolution at all. Okay. So far, I have been assuming that we have a single linear system. In a lot of practical applications, you combine multiple linear systems. You somehow connect them. And what is of great importance to us is to understand how to calculate the impulse response of the overall system. Let's say you have two systems. For each one of them, you know what the impulse response is. What is the impulse or response of the system that is made out of those two systems connected in series, connected in parallel, right? So let's discuss that for a little bit. So interconnecting. Connecting linear systems. Let's first look at parallel connection. I have two systems, S1 and S2. S1 has an impulse response H1 of t, S2 has an impulse response H2 of t, and I connect systems like this. The question is, what is an impulse response at the other? Now, if I present delta of t here, essentially presenting delta of t and delta of t. if delta of t is presented to S1 of t, you end up with H1 of t at the output. If delta of t is presented to S2 of t, you end up with H2 of t at the output. Therefore, the H of t here is going to be H1 of t plus H2 of t. So if you have two systems in parallel, the impulse response of the entire system is going to be sum of the impulse responses for the individual system components. So this system here, S, can be understood as having an impulse response that is equal to H of t, and it's sum of these individual impulse responses. The second common type of connection is your series connection. Right? In this case, you have two systems that are connected this way. This is S1 with an impulse response H1 of t. This is S2 with an impulse response H2 of t. Now what happens when I put the delta function at the input of this system here, which is now two of these guys connected in series? If I put the delta pulse here, what do I get at the output of the first system? I get H1 of t. Now H1 of t acts as an input into a second system. So what comes at the output? H1 of t convolved with H2 of t, right? So the overall impulse response here is going to be H1 of t convolved with H2 of t. If the duration of H1 of t is t1, duration of the H2 of t is t2, what is the duration of the overall? T1 plus T2, right? So you can see if you concatenate a lot of systems, your impulse response tends to spread in time. The third example that we're going to look at is what happens if you follow a system with an integer, right? So I have a system here S that has an impulse response H of t, and I follow this with another system that integrates from minus 0 to t dt, right? So what is the impulse response in this case? If I present x of t here, and I get here a signal y of t, then I know that y of t is going to be equal to x of t convolved with h of t, right? And my output here, let's call it z of t, is going to be integral from minus infinity to t y of tau, right? So that's the output of this system. Now if I switch things around, and instead of first running through a linear system, but instead first integrating and then presenting that to a linear system, this let's look at the result of that. So I have the same x of t presented, but first to an integrator that integrates from minus infinity to t, and then I present that to the same system S that has an impulse response h of t. Let's write out the output of this system here. Now, let's see, Z2. I can write here Z2 of t is integral from minus infinity to t, x of tau d tau, then everything convolved with h of t, right? Because I first integrate this x of t, and then I present this to a linear system, therefore the output is whatever comes out of the integral convolved with h of t. Go ahead.
What is inside the box? The first number 3, integral minus infinity to t.
Yeah.
What? It's like
It's an integral function.
Here?
no,
First,
no. The first top.
A limit, I think it's come out a limit.
Here. This one?
Yeah, what is it?
Is that parentheses?
Just a placeholder, right?
Yes.
When you don't have anything, you just say, there's something here that I'm integrating, right?
Oh,
It's not anything in particular. You have an integrator, right?
it's not 0, right?
No, it's zero.
It's not
It's
zero.
not-
If you want to say, okay, I'm
Yeah,
operating
function, right?
a function, and I put here a dot, say, give me whatever you give me, and then I'll crunch f of that, right?
Oh,
So here, this expects some sort of function, and then it will integrate, right? So it's nothing in particular. Whatever comes through the door will be integrated, right? Okay, but let's carry this, and then I'll explain to you why are we doing all of this. You know, it might be a little bit peculiar to say why are we even considering this system. And this is a system that has an impulse response followed by the integrator. And guess the next one is going to be system followed by the differentiator, right? So,
I got a quick question.
uh-huh.
Since we're dealing with linear systems, will the first case be equal to the second case?
Well, it's not obvious that that's the outcome. It is, right? That's what's going to happen. We're going to actually demonstrate that when you have an integrator, you can put it before or after, right? So, but that is not as a trivial, not such a trivial thing to see. What you're saying is that response of the system to an integral of an input is integral of the output, right? And you will see in just the next example, next type, that response of the system to the derivative of the input is a derivative of the output, right? So that's kind of not easy to see right away, but it turns out to be that way. You know, once you know the result, you can argue, okay, this is because the differentiation and integration is linear operations, right? So you know, when you feed it in a linear system, you can actually do them in arbitrary order. But we already kind of saw that, because remember when we were doing impulse matching for a system, we actually went and we proved that strictly, that remember the companion system? The companion system was the same system as the one that we considered, that had the same Q of D polynomial, but was not differentiating input, right? And then we were able to find its impulse response relatively easy. And then we said, well, we showed that the impulse response of the original system you can obtain by differentiating the impulse response of the companion system. Because the way they differ is that original system had P of D, meaning that it actually differentiated input before it was presented to the system. That was the whole derivation of how you actually get an impulse response in a time domain, right? So let's just go demonstrate this, and then I'll go back to that.
So, a quick question.
Uh-huh.
How will the system behave if we have a complex input signal, whereas the response of the system is real, or
No, the response of the system in general is complex too.
okay, and if the input signal is real and response is complex, so will it behave the same way, or
Well, you can get it straight from here, right? If the input is real and age of t is complex,
complex?
then this term goes away, and this term goes away. But you have this term and this term. So tell me what output is.
Complex again?
Complex, right? Complex, right? So now, can you? This may be a little bit tricky for the guys who haven't been in the communication systems of especially digital communication. What does it mean, complex signal, right? What is that?
It's a conjugate, it's always, it's a conjugate.
Where do we get complex signals all the time? Deal with complex signals. Hmm?
Capacitance, inductance.
No. This is you're talking about phasers and stuff. No. What I meant is remember how we signal in digital communications. What does complex mean? There's nothing really complex about it. It's just a notation of what how we're representing actually two real signals traveling in parallel. Yeah, there you go. The way how we signal in digital communication, we take two signals in parallel. One of them we call I signal, the other one we call Q. And then one of them we multiply with cosine, the other one we multiply with sine, and then put them all together. Now everything is real in this world, right? And then you kind of upband that and then send that through a channel that is also real, right? But what happens is, mathematically, it's much more elegant and easier to clean and notationally if you say, okay, what I'm sending is a complex signal that consists of two, xi plus jxq. And there's some math that shows that you can model the actual response of the channel as a complex response. Because what will happen at the output is exactly this. You will get the real part, which is in the branch that goes with cosine. You will get a mixture of the two signals that you sent. And then in the branch that goes with sine, you would also get a mixture of the two of them. And what our challenge is always in communication is to separate the two, right? And in a basic form, if you make sure that the phases are synchronized, then this term goes to 0, and then all of these cross terms, the x, let me see, these terms go to 0, right? And you have that, this term goes to 0, and then this term goes to 0, and then you get in a real branch, in I branch, you get your real signal back. In Q branch, you get your imaginary part back, your other signal that you're sending in part. So that's what it's meant here. Here, it's a little bit more abstract. We don't care. We just consider in general what happens if your input is complex and your impulse response is complex. Then you end up with 4 terms. But what is important about these all 4 terms, each one of them is convolution between two real signals. So, except for additional complexity in writing 4 instead of 1, there's really nothing much to be learned in terms of techniques. So that's why we restrict ourselves to real signals and just occasionally point to what happens when they're not real, when they're imaginary, when they're complex, right? Okay. So let's complete this analysis here. So now, if so this, after we can actually do some math, but I kind of shortened it here. This is integral from minus infinity to t x of tau convolved with h of tau. And this is essentially integral from minus infinity to t y of tau d tau. The claim here is what we concluded some few minutes ago, is that when it comes to integration, we can actually swap that with an impulse response of the linear system. We can take the signal, first run it through a linear system, and then integrate it, or we can do it the other way around. We can integrate first and then run the signal through the linear system. And the similar thing happens if your system is a differentiator. So response, we can actually interchange. Let me just put it as a note. Similar to 3 is the case when differentiator is put before or after linear system. So let me summarize this here. And this is the summary. If x of t has results in an output y of t, right, where of a linear system, meaning that y of t is equal to x of t convolved with h of t. Then we have two properties that we discovered by looking at the concatenation of the linear system with either differential or an integral. First one is the integral from minus infinity to t x of tau d tau would result in an integral from minus infinity to t y of tau d tau. In other words, the integral of an input results in an integral of an output. And then the second result is that the derivative of an input results in a derivative of an output. So those are the two properties that we discovered by concatenating these two. Another way to see why this is the case is using our commutative property of the convolution. The integration and differentiation are linear operators, right? So now you can see this as two linear systems. The overall impulse response of two linear systems that are put in series is the convolution of their impulse responses. And since the convolution is commutative operation, it doesn't matter which one you put first and which one you put second. And this is kind of taken here as a separate case because of the importance it has to us. We're looking at the differential equations and we're going to be utilizing this. You know, we actually already utilized it to derive the impulse response of a nonlinear system through impulse matching. Okay. So far, I've been looking at the delta pulse, and we look at an x of t. There's an input that is of a great significance to us, special form of an input, and it's called exponential. Right? We call it in the book. The author called it everlasting exponential. So let's take a look at what happens when we take a linear system and present it with everlasting exponential. So response of a system of the linear time invariant system to x of t equal to e to the st. This e to the st, everlasting exponential, means it exists for every t. It's not limited to t greater than 0. This s is usually referred to as complex frequency, and s we usually write as alpha plus j. So the input to a linear system is complex in this case. It is e to the alpha t cosine beta t plus j sine beta t. So there's I and q components there, right? Now let's see what happens when I present this signal to a linear system. I have a linear system S, and this linear system travels with this impulse response h of t. I present e to the st here, and I wonder what y of t is going to be at the output. I don't have to wonder much. I know that y of t is whatever is x of t convolved with h of t. In our case, this becomes e to the st convolved with h of t. Now, if I substitute what this star means here, this is an integral when tau goes from minus infinity to plus infinity, h of tau e to the s of t minus tau d tau, right? I'm using first commutative property of these two to swap them around, and then I have the integral when tau goes from minus infinity to plus infinity, h of tau, x of t minus tau d tau. Now you notice right away that this st it can come outside because it does not depend on tau. So I end up with something that looks like this, e to the st outside. And here I have tau goes from minus infinity to plus infinity, e to the s minus s tau d tau. Now look at this integral here. Does it depend on t at all? Is no. So what does this integral, what is this? When you do evaluation of integrals and you don't have t anywhere here, this will amount to a constant, right? It would be a single number, area under the curve of whatever this subintegral function is. So this is a constant value. It depends on whatever s is. Give me s, and I'll be able to calculate what this value is. So let's call this h of s. So let's go realize that this is a constant value. And let's call it h of s, and then I have e to the st. So we have a very interesting thing here. If my input is e to the st, what is my output?
How did you do that? Because I thought we were taking integration with tau, not t.
Correct, but look at this integral here. This is a definite integral. It does not depend on t, right? So for any given s, this will be an area under the curve, will be a single number, okay? So that's what all I'm saying here is that this is a single number, constant. It's a complex constant because this s is a complex number. In general, it will be something complex, but nevertheless is a constant, right? So now, if I realize that this is a constant, then I have something really special happening here. I have a function e to the st that when I present to the linear system, I get this function, the same function back, right? This function is special because when regardless of what the linear system is, if I feed in a constant exponential or everlasting exponential with a given complex frequency, what I'm going to get at the output is the same everlasting exponential, just scaled with some constant, right? This constant is complex, so it will add magnitude and phase, but nevertheless, this is going to be the same complex exponential at the output. Now, I already kind of mentioned that, and we all know that this is just a generalization of something that we already know. Let's look at a special case. Special case being s equal to just j beta, right? And that means I'm feeding cosine beta t plus j sine beta t. Essentially, I'm feeding in simple sinusoidals, right? And what this is saying, if you put a sinusoidal in the system of a given frequency, what comes at the output? The sinusoidal of the same frequency. This is a signature property of a linear system. This is how actually the easiest test that we have, one of the easiest tests in practice that we have if the system is linear. You feed a sinusoidal in of a given frequency, what comes out has to be a sinusoidal of the same frequency. What does the linear system can do to a sinusoidal? It can change its magnitude and it can change its phase, but it cannot change its frequency. If you feed the sinusoidal and you get at the output, you get sinusoidal or a bunch of sinusoidals that are of a different frequency than the one that you fed at the input, what do I know about the system?
Non-linear.
Nonlinear system, right? Now, this is a generalization. We're saying not only sinusoidal, this is a more general case. I can feed a complex exponential as e to the alpha plus j beta t, and I get the same complex exponential back. So,
Sir, then why do we use a linear system? We can use direct an amplifier if we just need a field, if we just need magnitude. Why to
Okay.
use such a complex linear
why
system?
do you use linear system, right? Different reasons. What is another way how we call linear systems are filters, right? So why do we use filters? All sorts of things, right? Now, you have both of them. When you say you just use an amplifier, is an amplifier a linear system?
Yeah. No,
It
depends.
should.
No,
There we
it
go.
depends.
We just said it. It
It
should
depends.
be. It should be. But is it? No. Because the way how we build amplifiers, we use a whole bunch of active components. Active components are notoriously nonlinear. If you look at transistor, the output is exponential, right? If you look at diodes or everything that's in there, you have some sort of nonlinearity. We spend a lot of effort making sure that what is our amplifier behaves as close to a linear system as possible. But it never gets there completely, or it gets there within a certain range, but then it flips, right? So outside of that range is nonlinear. So one of the common methods how we actually characterize the linearity of this one is through these tests where we feed in tones. There's a single tone test, two-tone test, three-tone test, where we actually feed in individual sinusoidals, and then we look at what are the byproducts that are being, do I have the mixing of them? How large is the mixture relative to the amplified signal? And then you can, we quantify amplifiers in terms of how linear they are. And that's a very, very serious practical issue, and we spend a lot of time trying to design linear amplifiers and trying to make sure that they are as close to linear as can be, right?
So one more question. That spatial signal that we to the power st, what is the practical application of that signal? Is it used somewhere? Because its
Well, what is the
amplitude is
signal?
rising exponentially every time.
E to the st
Yeah.
is equal to the e to the alpha plus j beta t, right?
Yeah.
So this is e to the minus alpha t cosine beta t plus j sine beta t.
Yeah.
So this, if alpha is negative, that's your dying exponential, right? That's a very common
Very common.
natural response of a system, right? The system starts, so whenever you have a complex roots, remember, of the characteristic polynomial of a differential equation, Q of d, then you end up with a natural response of this form. But the big point here is e to the st is special, right? And if you feed e to the st, you get it back, but just scaled by some complex constant. This h of s, we actually give it a name, and we call that transfer function of the system, right?
Excuse me, Professor.
Uh-huh.
So, based on you say we got about everlasting exponential, is it like imaginary thing, it's unreal system? So if it is everlasting exponential, it means imaginary thing. So we cannot make the system on that.
Let me ask you this. Is sinusoidal imaginary thing? Can you make sinusoid?
Yeah.
For limited time.
All right, limited time. What is limited time? Everything is limited. Our world is 4.6 billion years old, right? So nothing lasted forever. But if it lasted long time before, then you can approximate it assuming that it's unlimited, right?
So it's not like you have a sum of limit of the system, but it makes sense like everlasting exponential. Okay.
It's a philosophical argument at this point. What is everlasting, right? Nothing is everlasting, right?
But
If it's long enough, then we make it everlasting because our math simplifies, right? Tremendously, right? Because you have whenever you talk about system, you know, whatever you present, you're going to have, and we kind of alluded to that, you're going to have your, we call those transients and then steady state, right?
Yes.
And then if you're observing system for a long time, the transients are gone, so it behaves in a steady state, and that's that everlasting aspect of it, right? You know, so if the transients happened a long time ago, it might as well start a long time ago. And if it's long time ago, so that it does not impact the present, it can be very long time ago, right? You know, infinitely back in the past. Right? So that's what we're, you know, what we're here. We're after some elegant math, right? Nothing, and then you, in every particular scenario, you have to see how well does your approximation, where you say my sinusoidal lasted forever, fits. And in a lot of times it fits very well, right? If it's something is of the frequency of, let's say, 10 megahertz, and it worked for 2 seconds, that's, you know, what,
You can go
20
through that.
million cycles, you know, 20 million cycles before is when it started, right? So it might as well start infinitely in past. So this constant, h of s, is called transfer function. Of the system. And it tells us how does the system change the complex exponential or everlasting exponential at the complex frequency s. And as I said, this is for every given s, this is a constant. We have a couple of other definitions and the way how we can calculate this value. First one is, you can see that h of s can be even defined that way, is output signal over input signal when input signal x of t is equal to the e to the st. So if I feed e to the st into the system, and observe the output, divide the two, I'm going to get this constant h of s. Another way how, so this is the first way how we can evaluate it. Another way is if I know my differential equation, then I can get to that h of s directly from the differential equations. So let's see how we do that. Well, if you consider differential equations, of the system. And we start by saying Q of D applied to Y of T is P of D applied to X of T. Well, now we're making X of T special, and we can say X of T is e to the ST. So let's see what happens when I substitute it. I have Q of D times Y of T is equal to P of D applied to the e to the ST. But we know, since the system is linear, that Y of T is linear. Y of T has to be equal to h of s e to the st, right? Because for linear system, if you feed a complex exponential, then your output is going to be some constant times that complex exponential. So let me put this back in here, and you end up with Q of D times H of S times e to the st is equal to P of D operating on e to the st. Now H of S can go outside, it's a constant, and I can operate on these two functions. So if I do that, then I have H of S times this Q of D is d to the n plus a1 d to the n minus 1 plus and so on, an, operating on e to the s t. And I have this guy here as b0 plus, b0 d to the n plus b1 d to the n minus 1 plus and so on plus bn operating on e to the st. You have to be careful. One would be tempted to cancel e to the st. You cannot do that, right? Because this a q of d makes no sense on its own. It's just an operator, right? It's like saying something like this. Let me just say x squared is equal to y squared, and then you cancel these, right? That makes no sense. The same thing here. You cannot really treat these as nothing but just an operator, right? So now let's operate on this function here. So I have h of s. When I take the nth derivative of this is s to the n e to the st plus a1 s to the n minus sn minus 1 e to the st plus and so on plus a to the an e to the st has to be equal to b0. The nth derivative of e to the st is s to the n e to the st plus and so on, plus the last one is going to be bn. Now you can pull out e to the st and cancel it because you've taken all the derivatives. And what you realize is that h of s multiplying s to the n plus a1 s to the n minus 1 plus and so on plus an has to be equal to b0 plus b1 also b0 s to the n plus b1 s to the n minus 1 plus bn. And h of s is equal now b0 s to the n plus b1 s to the n minus 1 plus and so on bn s to the n plus a1 s to the n minus 1 plus and so on an. So the point here is if I have my differential equation here, I can directly calculate what h of s is from the differential equation. I would have to plug in s into my polynomial p of d. Instead of d, I put s. Downstairs, I have q of d, and I evaluate this. And for any given s, since a's and b's are constants, and s is a constant, this would give me a single number, right? So for any given s, this gives me a single number. Why are we spending so much time here? Because one of the reasons, not the only one, but one of the reasons is there's a Fourier analysis which will teach us how we can take any signal and decompose it as sinusoids. So what this taught us is that if I know my differential equation, finding a response of my system to a sinusoidal is a trivial task. I really don't have to do any calculation. I take the sinusoidal, scale it and phase it properly, and I'm done, right? Because I know that if I feed the sinusoidal, I get the sinusoidal of the same frequency. So now, if I'm going one step further, what we're going to learn is to take any signal and decompose it as sinusoidal. And we're going to do this to determine the output of the system to an arbitrary input. We're going to take the input, decompose it into sinusoidals, obtain the response for each one of the sinusoidals, and then put them back together to get my signal at the output. It seems a little bit roundabout, but it's the foundation of our frequency domain analysis. And that's what gives us also very much insight in a lot of problems, and we're going to be doing that for you.
So the input signal can be any signal.
Any signal, we learned that.
Yeah, it's like.
We learned that through Fourier analysis that you can take any signal and decompose it into sinusoids. And why do we do that? Precisely because of this. Obtaining an output of a linear system to a sinusoidal is a trivial task. There is no calculations involved once you know the transfer function. Okay. So let me give you some other problems here. Two dot four, 2, 3, 4, 5, 6, then 7, 8, 9, 12, and 13. Those are the problems that exercise this material. Okay. Any questions? That's it for the